Hello, my name is Rafał, and assuming that you're familiar with correlation itself, I would like to talk about cross-correlation. But as a quick recap, I will touch on correlation real quick as well. As we know, correlation is a measure of similarity of two signals, and the larger the value of the correlation, the more similar the two signals are. So for instance, I have generated three signals, A, B, and C, and we can visually tell that A and B are quite similar to each other. But signal C not so much, it's not similar to any of these. The formula for correlation is as follows. It's basically a summation of vertically aligned elements of the two signals. And because we're using discrete signals, this is the formula for it. But also, again, we're using MATLAB, so it has a different indexing scheme. So we're actually using this as the first element doesn't start at 0 but at 1. And capital N is the length of the signal. So if we correlate A and B, for instance, it's quite simple. So you take the first element of the first signal, you multiply it by the first element of the second signal, as we can see here. That's 5 by 3, which is corresponding to these. And then you add it with multiplication of the second element of the first signal by second element of the second signal, which is 10 by 9, as we can see that here. And you do that across the whole length of the signal. 8 by 6, 2 by 3, 9 by 9, 1 by 2, and 2 by 1. And that gives us a value of 244. Now, that value doesn't tell us anything just yet, because we haven't compared it to anything. So let's correlate A and C this time. We can tell visually that they're not similar, so we're expecting a smaller value, right? Yeah, we get 145 if we do the same thing all over again, but with A and C. So therefore, signals A and B are more similar to signals A and C. That could be very useful. Cross-correlation, for instance, is basically the same thing. All you're doing is correlating two signals at different lag values. So let's just imagine we shift the second signal all the way to the left, giving it a lag of -6 in this instance. So we correlate it. We multiply first element by the last element. So 5 by 1, which gives us 5. And we shift it to the right by one sample, or one lag value. We're at -5 right now. So all we do is we take the first element of the first signal and we multiply by the second element of the second signal. And we take the second element of the first signal and we multiply by the last element of the second signal. We can see vertically aligned. And we get a value of 20. And we shift it to the right by one sample again and again. And we go through it all the way to the positive lag value of 6. And when we plot the graph of correlation values versus the lag, we can tell at what lag value the two signals are most similar to each other. In this case, is at lag 0, which is a coincidence. It could be anywhere with different signals. And we get a value of 244, which what we got before, because them two signals are the same. Well, not the same, very similar. And therefore, we can tell that signal B is most similar to signal A at 0 lag, which just gives us extra information. So cross-correlation can be very useful. For instance, if you have a very noisy signal and you're trying to find an instance of a signal, let's say a peak in a different signal, you just cross-correlate it and you find it where it happens. So let's just imagine we shift the signal A all the way to the left and correlate it at each lag value. So this is the result we get. For 900 samples we get 0. That corresponds to nothing being here. And then we start correlating and we can tell that at sample lag 256 and 657 we get largest peaks. That's when it's the most similar to the second signal. And we know that the peak is in an offset of 47 samples. So we add them together to give us the actual position of that instance in the second signal, giving us 303, which is quite correct. And we do the same for the second. We found the two instances of that signal in the second signal. This could be very useful when it comes to ECG signals, as we can find P wave that we're very comfortable with, and we cross-correlate it with the entire ECG signal, and we can tell where exactly at what lag values that P wave occurs. So thank you very much.